So let's take a look at the following example prompt. So maltose is a disaccharide whose molecular formula is C12H22O11. Placing maltose into acidic conditions hydrolyzes maltose into 2-glucose sugars. Maltase, an enzyme that cleaves alpha glycosidic bonds, can also hydrolyze maltose into the 2 sugar molecules. Placing maltose into bromine in water produces a molecule known as maltobionic acid that contains this molecular formula. When maltobionic acid is mixed with methyl iodide in base and is then hydrolyzed, we produce 2 molecules, 2,3,4,6 tetramethyl-D-glucose and 2,3,5,6-tetramethyl-D-gluconic acid. What is the structure of maltose? So we want to use each one of these pieces of information to basically construct what the structure of maltose is. So let's begin with each sentence and see what each sentence tells us about the structure of maltose. So sentence number 1 tells us that maltose is a disaccharide. We contain 2 sugar molecules that are bonded via a glycosidic bond. Now, we do not know the type of glycosidic bond. That's what we want to basically determine. So, placing it into acidic conditions hydrolyzes into 2 glucose molecules. This tells us our 2 sugars in maltose are glucose sugars. So maltase, an enzyme that only cleaves alpha glycosidic bonds, also cleaves maltose. That basically implies that our orientation of the hydroxyl group on the first sugar glucose molecule is in the alpha direction. Now, placing maltose into bromine in water produces a molecule called maltobionic acid. This basically means our sugar can be oxidized. It's a reducing sugar, and so that means it contains a hemiacetal section on one of those glucose molecules in maltose. Now, when we take maltobionic acid and mix it with methyl iodide in base, basically all the hydroxyl groups that are free on our maltose will be methylated. When we hydrolyze that methylated maltose, we then produce this molecule and this molecule. And we want to determine what the structure is. Now, let's use this last piece of information to figure out what the structure is. Let's draw these 2 molecules. We have 2,3,4,6 tetramethyl-D-glucose. So, we have carbon number 1, we have carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6. Now, carbon number 1 contains our aldehyde group. Then we have the connection between these carbons here. Carbon number 2, carbon number 3, carbon number 4, and 6 have all been methylated. So we begin with carbon number 6, and this has been methylated. Now, we're dealing with a D-glucose sugar, so that means this O will point to this side, and this one is this one is not methylated. Here, we have our hydroxyl group because this is carbon number 5. Now, carbon number 4 is also methylated. Carbon number 3 is also methylated, and carbon number 2 is also methylated. So this is our 2,3,4,6 tetramethyl-D-glucose. So 2, 3, 4, and 6 tetramethyl-D-glucose. Now, what about the other molecule? Molecule 2,3,5,6 tetramethyl-D-gluconic acid. Gluconic acid simply means our aldehyde group has been converted into a carboxylic acid group. So we have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So now we have an OH group here. Now, carbon number 2 has been methylated. Carbon number 3 has been methylated, 4 has not been methylated. So this is, so it should be, this should be an H. H. So 1, 2, 3. So 1, 2, 3, 4, and this has been methylated, and so is 6 methylated. We have the bonds here, and let's label our carbon. So we have basically carbon number 5 that is not methylated, and this is carbon number 1, and carbon number 4 here has not been methylated. This contains an OH group, and this is 2, 3, 5, 6 tetra methyl D-gluconic acid. Okay, so basically using this information we can determine what the bonding is between our two sugars. So we're basically working backwards. So when we obtain these two molecules, we basically hydrolyze the methylated maltobionic acid. So now if we go in reverse, if we connect our molecules, the connection, our glycosidic bond is between the first and second molecule. So on the first molecule, it's this carbon here that is connected, and it must be connected to the second in the region onto the carbon where we basically have our hydroxyl group. So basically this is our connection here. So this one is not methylated because this is the carbon that basically forms our cyclic ring. So when this hydroxyl group attacks this carbon, it forms that cyclic 6-membered ring of our glucose molecule. Actually, more specifically, it's this oxygen that will form a bond with this carbon here. So let's actually draw the three-dimensional structure. Oh, and by the way, we also know that this has to be oriented in the alpha position when the cyclic ring is formed. So when the cyclic ring is formed like so, this should point in the alpha direction because we know that maltase basically cleaves maltose, and maltase only cleaves alpha glycosidic bonds. So the structure of the molecule looks something like this. We have the oxygen here, and then we have so basically this is what our maltose looks like. So this is this molecule here. This is carbon number 6, carbon number 5. This is carbon number 4. This is carbon number 3. Carbon number 2. Carbon number 1, which is this carbon, contains this hydroxyl group that points downward. Now, this is carbon number 4 of this one. So we have carbon number 1, carbon number 4, and this is the alpha position. So this is an alpha 1,4 glycosidic bond. So let's finish the rest of the molecule. We have an H here. We have an H pointing up here. We have our other groups here. And we have our OH here, the H here, the H here, OH here. Now, the only thing that we really don't know is where the OH points on this carbon number 1 of this molecule here. So the way that we symbolize the unknown factor is by using a squiggly line. The squiggly line means that the OH can point up, in which case it will be the beta version, or down, in which case it will be the alpha anomer. So this is our maltose molecule. Now let's just make sure. So basically, when we take our maltose and we place it in bromine in water, that produces a molecule called maltobionic acid. So this information means this molecule is oxidizable. So we can oxidize this molecule. It can act as a reducing agent. It is a reducing sugar, and that means it must contain a hemiacetal group. Now, sugar number 1 does not contain a hemiacetal group, but this does contain a hemiacetal group. Let's suppose our OH points upward. This is the hemiacetal carbon. So we have our hydroxyl group here and our alkoxide group here, OR. And so that means this is the hemiacetal. And when we mix it with bromine and water, what basically happens is this hemiacetal section basically exists in an equilibrium with the free aldehyde form. So this section of this molecule can basically open up and we get the following diagram. So this region becomes an OH and the bottom region basically becomes an aldehyde group. So I'm not going to draw the rest of the molecule. You can imagine that this bond is this bond here, and this section is this section here. Now, if we basically place bromine in the presence of water, this aldehyde is transformed into a carboxylic acid, which looks something like this. So we have one more additional oxygen atom on this molecular formula, and so that's why we have the additional oxygen atom here. So this is how our maltobionic acid will look like. So we can draw the rest of the molecule, which I'm not going to do. You can draw that in yourself, but basically it's going to look something like this. You could fill in all the other groups as well, and here we have the other sugar molecule with our O here. So you can fill in the other groups. Now, if we take this, actually, let's go ahead and fill the groups because that will give us some more insight into what happens when we add the next few reagents. So, okay, so this is our OH, OH, H, H, OH. Okay, so this is the maltobionic acid. Now, when we take maltobionic acid and we mix it with methyl iodide and base, all the free hydroxyl groups are basically methylated. So this hydroxyl group is methylated. This hydroxyl group is methylated. This one is methylated. This one is methylated. And the same thing is true for these. This is methylated. This is methylated. This one will be methylated. This one here will be methylated. This one will not be methylated because this is a carboxylic acid. So basically, when we take the methylated maltobionic acid, we hydrolyze it, we produce the 2,3,4,6 tetramethyl D-glucose, this molecule, and the 2,3,5,6 tetramethyl D-gluconic acid. So when we can imagine that we basically break this bond here, and what happens is this molecule here, so that's this region here, so this oxygen will basically end up on this location on sugar molecule number 1, and this will transform into an aldehyde group, and this oxygen here attached to carbon, so this is carbon number 5 and carbon number 1. So carbon number 1 will contain the aldehyde, and carbon number 5 will contain the O and the H. And that's why we have this section here. Everything else will be methylated. In this section, when this breaks off, this carbon will gain the OH. So this carbon, that's carbon number 4, will have the OH, and everything else will have the methylated region, and this will be our carboxylic acid. And this is exactly what this molecule actually looks like.